And medians go from the vertex of the triangle to the opposite side, and they cut the side in half, which in geometry we call bisecting. Bisecting means like you cut it perfectly in half. So that's how you know what a median is. It goes straight to the other side. It doesn't necessarily cut it like perpendicularly. It just like kind of runs into the other side and it cuts it in half. So that's what a median is. And then we learned that the orthocenter is where the altitudes are concurrent. So concurrent means that all three of them intersect at the same point. And we know that altitudes are perpendicular to the other side, but they still go through the vertex. So you can think of it as like the height of the triangle, kind of, if each of the sides was like the base. So if you have this as the base, then this is the altitude of the triangle, so from that side straight through the vertex. Or you can spin the triangle on its side and say, okay, this is the base, now this is the height of the triangle going through the vertex. Or you could spin it around on the other side and say, okay, this is the base this time, now this is the altitude. Or like this is the height of the triangle. Okay, does that make sense so far? We're good so far? Okay, so now we're going to move on to the circumcenter, which kind of ties the two ideas together. So the circumcenter is where the perpendicular bisectors are concurrent. So they are perpendicular, so it's kind of like an altitude because the line is perpendicular to the side. And then they're bisectors, which means they cut the side in half. So the thing that is different about these is that they don't necessarily go through the vertex. Does that make sense? So the thing that was true about the other two is that the median went through the vertex, the altitude went through the vertex. Both of those went through the vertex. So now we're saying, okay, we're going to keep the part where it cuts it in half, we're going to keep the part where it's perpendicular, but we're going to take away the part where it has to go through the vertex. Does that make sense? Okay, so we're going to say a circumcenter is where the perpendicular bisectors, or the perpendicular bisectors, are concurrent. And just remind yourself, perpendicular means that you've got 90-degree angles. That was something that a lot of students, when I did this with fourth period yesterday, a lot of students had forgotten that's what perpendicular means. It's two lines that are coming together at a 90-degree angle. So if you look at these different examples, you can see, like right here, we have this side from C to B, and then we have a line, and that line cuts it perfectly in half. Do you guys see that? It cuts it perfectly in half, and then the line for the side and the line that cuts it perfectly in half, they come together at 90-degree angles. Now, this line that cuts it in half, it doesn't necessarily go through the vertex. So they could go through the vertex, but they don't have to. And then we've got this line over here, it cuts it in half, it's bisecting it, and it's perpendicular as well. Again, it doesn't quite go through the vertex. And then the last one, again, we have the side, it's cut in half, it comes together at a 90-degree angle, and it doesn't go through the vertex. So we've got perpendicular bisectors there. So the circumcenter is also the center of the circle, and it can be, it's the center of the circle that can be circumscribed about the triangle. So this is kind of interesting. If a circle is circumscribed about a triangle, it means that the corners of the triangle, or the vertices, that's what we call them with a triangle, we call those corners. We don't call them corners because there's not 4 of them. We call them vertices instead. Those vertices can touch the circle. So if you have a circumcenter, if you found the circumcenter of a triangle, that circumcenter is also the center of the circle that would go around the triangle and touch all 3 of those vertices. And that would work every single time. Okay, so what I want you to do is, if you have a color nearby, or if you don't have a color, borrow one from somebody. I want to show you guys something interesting. We're grabbing a color. Okay, so what I want you to do is take your color And we're going to put a dot where the circumcenter is. And then we're going to put a dot on the edge of the circle where it touches the triangle. So you're going to notice that's a vertex. And then we're going to draw a line between the two. So from the center to the edge of the circle, which also is the vertex, and this is going to be the radius of the circle. And then we're going to do that all the places where we can see the same thing happening, okay? So from the center to the edge of the circle, which is also where the triangle touches it, that's another vertex. That's a radius of the circle. From the center of the circle to where the vertex touches, there's a radius. And so when we run into these problems where they give us that we have 3 perpendicular bisectors, this is a habit that we're going to get into. We're going to draw from the circumcenter to the vertex, and we're going to say it's a radius, it's a radius, it's a radius, and we're going to draw the circumscribed circle. Because this is something they typically don't label, but because all 3 of these are a radius to the same circle, we are going to know, oh, those 3 are going to be the same length, right? Because a radius to the same circle has to be the same length. Does that make sense? Okay, so let's fill in this other blank up here. The vertices are equidistant from the circumcenter, and that's because the circumcenter to the vertex is the radius of that circle. Circumcenter or vertex? Equidistant. Equal distance. Yeah.
Radius.
Equal distance. If you don't like the word equidistant, you can write equal distance instead.
I like it.
Yeah, you like it? Okay. Yeah. Yeah, it's possible, yeah. If you don't see it written out, you might think I just said equal distance weird. Yeah. Yeah, equidistant is equal distance, but mathematically written together. All right, so from the vertex to the center is the radius of the circle, which is how we know this fact for this. Now, the circumcenter doesn't have to be inside a triangle, which is probably everyone's least favorite part of this, because it seems like if you have a center of a triangle, if that's what we're studying right now, is like, oh, these are different centers of triangles, then the center of the triangle should be inside the triangle. That just seems like common sense. But if you have an obtuse triangle, then the circumcenter is actually outside the triangle, which is very strange. But it works. If you were to find the center of the triangle this way, it would end up being outside the triangle. And according to the math, that's okay. By the definition of how it works, that's totally fine in a situation. Now, the part that is my favorite about this is over here. If you have a right triangle, so if you have that 90-degree angle, then your circumcenter ends up being in the very middle of your hypotenuse, which I think is kind of cool. So any right triangle, if you found the circumcenter, it would be in the middle of the hypotenuse. So middle of hypotenuse. So that's kind of a neat little factoid. I like it. It's fun. All right. So those are all the different facts that we have about circumcenters. Now, this next part has this name right here. Does anyone, it has to do with the letter E. Euler. Yes. I know it's very tempting to say Euler, and that would be very American of us to butcher a name that is not American. But we have to be better than that. So we're going to write above this.
The author invented Euler's number, which is Euler's number is famous.
It's famous, but it's not aesthetically pleasing. I mean,
it's defined by
A pretty number would be like 3.
to create a shape.
I prefer Avogadro's number.
I like Avogadro.
Do you like it because it said Avogadro? What is Avogadro's number?
Yeah, what?
6.02 times 10.
Okay.
But
Alright.
I love
Okay.
my favorite number is Graham's number, but the largest number that has any meaning. No, like the largest.
So
number.
technically infinity is a concept, not a number.
It's,
Now, does Graham's number have anything to do with a graham cracker?
I don't think so. I
I
believe it does something about hypercubes.
What about Teddy Grahams? Let's move on.
Yeah,
All right. Leonard Euler noticed a relationship. Now, this is not.
It's large enough that if you tried to store it on a conventional computer, then it's required would turn it into a black hole.
Interesting. So this part right here is not on the EOC. I just found it when I was researching for this unit, and I thought it was really neat. So this is you will not be tested on this, but it's kind of cool. So Leonard Euler noticed a relationship between the 3 classical triangle centers. They are collinear. Collinear means they're in a straight line always. Like if you were to draw any triangle ever in your life that you could possibly think of, and then do the math to find the orthocenter, to find the centroid, and to find the circumcenter, you would always find that they end up being in a straight line. Every single time. No exceptions. It would happen with every single triangle you draw, which is like mind-boggling, but that's not the whole piece of the pie. I'm hungry. Anyway, the centroid is always in the middle of the other 2. So this is how the picture always works. The centroid is always in the middle. If you were to go through and draw any triangle you could think of and you found it, the centroid would always be in the middle. And then the distance between the centroid and the orthocenter would always be 2 times the distance between the centroid and the circumcenter. Always. It would have a 2-to-1 ratio every single time. And they would be in a straight line. I don't know. Let's ask him. He's dead. We can't. All right. The line that these 3 centers of triangles lie on has been dubbed the Euler line. You don't need to know that. I just thought it was cool. Okay, turn the page. All right. This next one is not a classical triangle center, but we study it anyway because it's also interesting. So this is called the in-center, and it is where the angle bisectors, so not line bisectors, not segment bisectors, but the angle bisectors are concurrent. So where the angle bisectors are concurrent. So I'm going to show you guys how they often draw this in a picture. So you can see like here we have all of angle C, and then they broke it down into angle 1 and 2. When you show that 1 and 2 are congruent, you would do like one little arc, one little arc. There's me showing that 1 and 2 are congruent. And then for all of angle A, they broke it down into angle 3 and angle 4. If I want to show that these 2 are congruent, then I'll put 2 little arcs. Those 2 angles are congruent. And then they have angle B. They broke it down into angle 5 and 6. And then we could draw 3 little arcs, and then we're showing the angle 5 and 6 are congruent. Yes?
Why is that not a classical triangle center? It doesn't seem any different from the circumscribed.
I think there's like, I don't know how many there are, but when I was doing research, there was like a lot of different triangle centers. I think it just wasn't included in the...
that long for Euler to make his own favorite thing. Like, it seems pretty obvious from like doing a demonstration on the subject.
Pretty obvious. Well, collinear is kind of a big deal because that's a straight line. That's not like, oh, they're in a row, but they're in a straight line every single time.
It seems like the first person to do a presentation on different triangle centers would have noticed it, just because you take a triangle and you mark all 3 different centers.
They probably weren't doing a lot of presentations on triangle centers.
How do they teach people? Like it seems like somebody would have noticed that.
Well, there's a difference between going like, oh, these are like, I've noticed a coincidence versus I can absolutely say this is true in all cases.
Did nobody see that one? I think Euler had OCD. That's why he has all the visually appealing.
I mean, it's possible. Yeah, you are welcome to look it up and let us know what you find.
What's the difference between concurrent and congruent?
So concurrent just means that they come together. So it's like an intersection, but it's an intersection of more than two. And then congruent is saying two things are mathematically equivalent. Yeah. All right. So I think the reason that I think that this one is not considered a classical triangle center is because the classical triangle centers always have to do with segment lengths, and this one has to do with angles, which I think is why it's not included. But it's common enough as far as being considered the center of a triangle that people usually study it as like being one of the typical ones, even though it's not considered classical, which is why we're going to look at it too. So with this one, very similar to the idea of circumcenter, the incenter is also the center of the circle that can be inscribed. In the triangle. So when you have a circumscribed circle, the circle is outside of the triangle, and you have the vertices are touching the circle. When you have an inscribed circle, the circle is inside the triangle, and it's the sides that are touching the circle. Does that make sense? You have the sides touching. So let's go ahead and grab our markers or colored pens or whatever you have. So we're going to draw a dot at the incenter. And then this time it's going to go to the edge of the triangle and go to the edge of the triangle. So you can see that instead of drawing it from the center of the triangle to the vertex, you're drawing it from the center of the triangle to the side of the triangle. See the difference? So when we look at the last one that we did, our radius was from the center to like the corner of the triangle. Now we're going from the center to the side. And then for each of those, we're going to label it's a radius, it's a radius, it's a radius. And so if all of those are a radius, that means all of those are going to have the same length. They're going to be the same. So we're going to say that the sides of the triangle are equidistant from the incenter. All right. How do your brains feel about that? You feel okay? All right. So this set of notes was kind of laying out all the different facts that you can know about the different centers. Within these, there are some different things that we saw where the math could be involved. So for example, we had angles are cut in half. You can get some numbers there. We have a radius there. You can get some numbers in these problems. We have a radius on this. We can get some numbers there. We have sides that are bisected, so sides that are cut in half. There's room for us to have numbers, so there's some math problems we can get. But this whole packet was full of random facts. So for a circumcenter, it can be outside of the triangle. For the orthocenter, we can see that the orthocenter looks like it needs to be... Wait, the orthocenter doesn't have to be inside the triangle? Was that the blank that we had? That was from last night. So those are some of the random facts. So when we study this, and when you guys are questioned on it both for my test and for the EOC, the questions are a mixture of facts that you memorize, and then some... Oh, like this. This is it's the obtuse, yeah. Yeah, because it kind of creates a triangle when you draw the altitudes. Yeah, the altitudes feel like they're part of the triangle. So there's kind of a mixture of some questions that are just asking you for facts, and then some questions that are asking you to do math. So the next thing that we're going to do is we're going to take some of these facts and we're going to see which ones of them can be turned into math problems. And then after we do some of the mathy types of problems that you can do with this, then I'll let you guys actually get started with some practice problems so you can see what it would look like in a situation where you're actually putting this into practice. So this is something that you for sure want to make sure you get on your cheat sheet, because obviously we took a lot into our brains today, right? So you want to make sure that you get all of this down in a lot of detail. Either you take it straight from your packet and put it on your cheat sheet, or you get on Canvas and look at the cheat sheet video, okay? But some way or another, you want to make sure you get this stuff on your cheat sheet, because this is stuff that you're definitely going to forget come the test day. And I don't remember, you guys are a day off from 4th period?
We are. It says it is on Friday.
So I think you guys are on Monday.
I'm not gonna be
Yeah. Yeah, because you guys will be.
Are you sure? Can you check though? Make sure.
Yeah, I will check, but I'm almost positive you guys are Monday.
I just think it's
Not
like,
you.
you should like a small or like. I don't know. I make mine.
If it's a little big in one section, you have to make it a little small in another section so it still fits on a page. Okay. So go back to the first part of your notes from last night. We're starting back again at the centroid. It says to find the coordinates of the centroid, and that is in the notes from last night. So how do we find the coordinates of the centroid? When working in the coordinate plane, yeah. Perfect. So we're going to find the average of the x's, find the average of the y's. So we're going to add up the x coordinates, add up the y coordinates, and divide by 3. So let's write down the coordinate for G. We have right 2 and down 4. H is left 1 down 7. I is left 4 down 7. So we're adding up all of those x coordinates. And dividing by 3 to find the average. -1, perfect. -6. Anyone else want to confirm, are we getting -6? -1, -6?
Hey, it's inside the triangle.
Yeah. Is centroid one of the ones that always has to be inside the
I
triangle?
believe it is.
Yeah.
Yeah.
This is the one that's the center of gravity, right? The centroid, the center of gravity. So it would make sense that has to be inside the triangle.
Or that would be the geometric one. The geometric center. Then. Right.
Yeah, if
So
it's the
the
center of
average-
gravity.
The average of all points.
So if it's the center of gravity, it would have to be on the triangle because you'd have to be able to actually touch it if you had the physical triangle in front of you. Yeah.
Oh, it's not really.
Yeah. Okay, so the next one is talking about, we've got the outside side length. So again, we're still looking at our notes from last night. So if we look at the outsides, we're using the fact that we have the medians. So the medians touch the sides, and what do they do to the two pieces? Yeah, it's bisected, right? So if this is 8, then what's this over here? 8. Okay. All right, and then we also know that the centroid divides each median. So right here, this is that point, that concurrent point where all the lines come together, and we know that it divides it into a ratio. What's the ratio? 2 to 1. Okay, so the 10 is AG. This is 10 right here. So if this is 10, it's a 2 to 1 ratio. If this is 10, what's this? 5. Okay, there's our 2 to 1 ratio. Now, this is a typo on the notes. My picture got too close to this, so you can't see the number, but CD is supposed to be 18. And so the strategy that we can use anytime they give us the entire median, which is what they did for CD, they gave us the entire length, is we can just use a variable to do that 2 to 1 ratio. So from C to G is the 2 part, so I'm going to write 2x. The G to D is the 1 part, so we've got our 2 to 1 ratio, 2x to 1x. So if we know the whole thing is 18, then what should we do? Yeah, so we can do 2x plus 1x equals 18. So we got 3x total. And so what is x? X is 6. Good. Okay. So we have x is 6, and then what's the 2x part? 12. Okay, so let's go through and then fill in all of these segments. So BD is 8, and AB is, okay, and EG, okay, and AE, okay, and CG, and then DG, 6. Okay. Any questions there for centroid? The mathy part is good? We feel good about numbers? Okay. All right, so the next part is circumcenter. This is where we have the perpendicular bisectors. So similar to centroid, we are cutting the sides in half, but we're not going through the vertex when we do it. We're cutting the sides in half. We're making those 90-degree angles. If we look at our notes, what is the thing that we're supposed to add into each picture? What are we supposed to draw? Yeah, so we're going to draw the center. We're going to go from the center to the, to each vertex. Perfect. So center to the vertex, center to the vertex, center to the vertex. So this is the one where we have that circumscribed circle, right? So I was going to say the circles are really hard to draw. Whoa. That's pretty good. The circle's kind of
My circle
lumpy.
looks like an oval, like it's like crooked.
You know what? It doesn't look because you're used to boxing.
It looks like an asteroid.
You've drawn too many
It
boxes.
looks like an asteroid.
People who normally circle their answers, are your circles better? No?
Yeah, because there shouldn't be anyone in here circling.
We should all be boxing? We should all be rectangling our answers? Okay. So this is where we are. So let's label. Now that you have the circle drawn in, it should make some of the things easier to find. So we know that the line here is a perpendicular bisector. So if this is 20, what's this? 20. And if this is 15, what's this? And if this is 24, what's this? Okay. And if this is 25 and it's a radius, then what are these two? Okay. And then, so all of these, this was a perpendicular bisector, and this was a perpendicular bisector, and this is really little, but it's a perpendicular bisector too. And so what are all these angles in here? Yeah, they're all 90, so I'm going to go ahead and draw those in. 90, 90, 90, 90, 90, 90. Okay, so let's go through, now that we have that picture, and let's write our information. So from A to G is 25. B to D, C to F, 24. Okay. A to B, 40. C to E is 15, good. A to C, the measure of angle A to D to G, 90 degrees. So A to D to G is this one right here. So whenever we have the 3 letters for the angle, you're basically looking at the middle letter. So ADG is this one right here, that's 90. Okay, and then BG, what's BG? 25. Okay, so we're going to say 2x minus 15 equals 25. And then what do we have to do to solve that equation? Okay. So 2x equals, okay. And then what do we do? Okay. All right, do we need to repeat any of them? No, we're good? Okay. Go ahead and flip. All right, so I want you to take your color and draw a dot on the center, and then draw a dot on each vertex, and draw your circle. So draw a line from the center to each vertex, draw each radius, draw your circle.
Okay, man. Good boy.
The circles are hard to draw, huh?
Our class is going to do a little, just like
What was some kind of little poo thing? You know that app you have to take care of?
Did you say the poo thing?
Yes.
Mine looks like your mom.
Yes, every day she's like, poo off.
Mine looks like a really healthy potato.
Yeah, mine looks like a deformed cartoon.
No, that's an egg.
No, an egg would have.
It's okay. All right, so now once you drew it, are you able to see what your different equations should be? Yes. Okay. So what should our equations be? Okay, so 5y minus 6. 5y minus 6 is a radius. 24 is a radius. Okay. What else do we have? 8x plus 16 equals 24. So 8x plus 16 is a radius, 24 is a radius. Okay. Okay, and then these two, they're not a radius, but that side is bisected, so those should equal the same thing too. Right here. So these two are the same. Okay. And then these are going to be pretty simple for us to solve, right? Okay. Are we getting those okay? Brains are good?
So, oh, I see. You draw a strike through it. I did it without the strike, and it looks like I just wrote 2 equals 2 when I filled out.
So a lot of math people will cross their Z's, and that's why. Or else they'll really do their the loop in the 2 with the loop in it. Or do like cursive Z's or something. But I started crossing my Z's when I was like really solidly becoming a math teacher, just as a way to differentiate them. Habit. Well, because most of the time, I don't do a lot of writing that's not math. So most of the time, if I write a Z, it's because I'm doing math.
Yeah, have you written, is it possible that you've written more math symbols than regular letters? Like, I wonder what percentage of the population has written. What percentage of the population?
Well, I'd say like most of my friends who are adults like do not handwrite at all. Like cannot remember. And I'm like, I handwrite all the time, but it's because I make answer keys. So.
Everybody did like.
I do not understand what's going on right now.
I don't want to.
Are you just checking to see how?
We can move and just start pointing.
All right, let's move on. Okay, so in center, if you guys notice, we skipped Orthocenter. It's not that there's no math problems for it, it's that the math problems that are for it are beyond this class. They're like pre-calc level, and so we don't do any math problems in this level. So in this level, you just have to go like, is there an altitude there? Yes or no? Is it one of the ones that is inside or outside the triangle? That's like, you just have like 2 math facts that you know about it, and then other than that, that's like all you can do with the Orthocenter. So that's kind of nice. All right, so the in-center says in the diagram below, we have an isosceles triangle. Does anyone remember what an isosceles triangle is? Say it again, CJ. Yeah, one angle's different, but 2 are the same. So they usually say like the base angles are the same, and then what else do they say? 2 base angles are the same, and 2 sides are the same.
Oh, okay.
So 2 angles are the same, 2 sides are the same. So here they said that AB is the same as CB. So this side right here, AB, I don't really know. So I'm just going to say this. And by this line, I mean the whole side. That whole side is the same as that whole side. And if these 2 sides are the same, that means that this whole angle and this whole angle are the same. That's what that means. Okay. You have angle bisectors, AD. So AD is a bisector, so that means that this angle Those two are the same. And then BF, so this is a bisector, so these two are the same. CE is a bisector, so these two are the same. Well, my markings look kind of similar. Okay. And then now this is an incenter. Okay. So they said the measure of angle BAC. So from B to A to C. So this entire thing is 50. If the entire thing is 50, then what are the individual angles? Okay, so I'm going to go ahead and erase this. And I'm going to write 25, 25. Okay, and then since the base angles are the same, then what does that tell us about the other side? They are also going to be 25 and 25. And then overall, that's 50 for the whole thing. Okay, now they want us to find the measure of angle AXC. So AXC is this angle right here. That's the one we don't know, AXC. So how could we find the measure of angle AXC? Well, 50 is the top and the bottom together. Okay, so we'll do 180, take away. Yeah, my labels might be confusing.
Wait, 180 minus 25 minus 90?
AXC is both sides.
Oh, I see what you're saying. Alright, I was calculating the individual sides then definitely.
Yeah. Okay, so 180 minus 25 is 130. So 130 is the whole thing. So the measure of angle AXC is 130 degrees. Okay. For the next one, it says we have an incenter. So since we have an incenter, on this one, the first two things they're asking us to do have to do with lengths. And since they have to do with lengths, we're going to go ahead and draw the picture. So we're going to start off by drawing the center. And then for this one, do we go from the center to the vertex, or do we do something else? Go from the center to the sides. That's our circle. Center to the side, center to the side. And when they draw those 90-degree angles, what they're showing you is they're saying, hey, we went straight from the center to the side, we went directly there. So you can tell that they did the shortest distance.
That does not look like it's going to break. I tried to find like a structure for that, so then I just started drawing.
Do some more on it. I like.
Yeah. Oh, whoa, that's a good circle.
Yeah.
Thank you. Okay, so I went ahead and I labeled each radius as the same. So, what's the length of ST? And what's the length of TU? So I've got 15 equals 2x minus 1. And then I can go ahead and solve for x. Okay, and then for the next question, it says PRT. So from P to R to T, PRT is this part right here. PRT is 24 degrees. If PRT is 24 degrees, then QRT is what? It's also 24 degrees. They got to be the same. Okay? The next one says from R to P to Q. So R to P to Q, that's this whole thing. If RPQ is 62 degrees, then RPT is just this part. Then RPT is how much? 31. All right. Does that make sense? Yes? Brains are good.